Imagine standing in a quiet bookstore, just watching the patrons browse the aisles. After a few weeks of observation, you notice a distinct pattern. On days when it rains, customers are far more likely to stop and pull a specific green book off the shelf. It is a deeply human instinct to look at that data and assume a direct link. We see the rain, we see the reading, and we conclude that the weather makes people want to read that particular book. In statistics, this is called an observational study. This diagram shows what is actually happening. We see a link between rain and book views, but we're missing a hidden variable. When it rains, people step inside to wait out the storm. They stay in the store longer. That extra time spent wandering the aisles, not the rain itself, is what actually leads them to the green book. These hidden variables, known as confounding factors, make it difficult to trust historical data. If you are simply watching a system without touching it, you can never be entirely sure if A caused B, or if a third factor caused both. You cannot optimize a digital platform, deploy a medical treatment, or make high-stakes decisions based on a coincidence. To find out what actually drives behavior, we have to stop watching and start interfering. This is where we introduce the A/B test. It is the mechanism that bridges the gap between noticing a pattern and proving a cause. Look at this model. We take our incoming traffic, store visitors, app users, or patients, and force them to diverge. One path is the control group, representing the status quo. The other is the treatment group, where we introduce exactly one intentional change, like moving our green book to the front window. This structure relies on strict randomization, like clinical trials using a coin flip for placebos. Assigning groups randomly neutralizes outside biases, distributing factors like weather or mood equally. Because groups are identical except for our intervention, any outcome difference is attributed to our change. Creating two identical, competing realities allows us to strip away the noise of the world and measure the specific impact of a single choice. Let's say you start your test, and within the first hour, the group seeing the green book in the window pulls it off the shelf 10% more often than the control group. The temptation is to celebrate early, shut off the test, and deploy the change to everyone. But that is a mistake. Drawing conclusions from a small sample size is risky. If you flip a coin and get 3 heads in a row, you don't assume the coin is rigged. You just haven't flipped it enough times to see the averages balance out. In statistics, every experiment starts from a baseline assumption called the null hypothesis. This is the default stance that your intentional change actually did absolutely nothing. The rest of the A/B test functions as a trial. The burden of proof rests entirely on the new data to show that the outcome wasn't a fluke, disproving the null hypothesis in the process. In the early stages of an experiment, a genuine breakthrough is often indistinguishable from a random statistical fluke. As data points accumulate, the early chaos of random chance smooths into 2 distinct bell curves. Look at the physical distance, the delta, between these curves. This is statistical significance, proving the odds of this difference happening by pure accident are incredibly low. At this point, the null hypothesis is rejected, the winning variation is crowned, and the change can be safely deployed to the entire population. This provides a rigorous framework for identifying cause and effect. It allows us to move past events that merely happened alongside one another and start identifying outcomes that followed because of our change. This methodology works when we control a static environment. But how do we measure what's happening when the environment itself shifts under our feet?